In the last segment, we talked about how to make our Lewis structures. Sometimes we have resonance, such as nitrate, in which we have electrons moving from different places, but the arrangement of the atoms have not changed. We're also going to be looking for what we call isomers, in which we're looking for different arrangement of atoms. There should be a molecular models or molecular geometry or VSEPR sheet or something like that in your Blackboard shell where you've been given instructions to complete all of those structures. So you should have done that, and now we're ready to move on to segment 8. Okay? Now, figuring out the structures are great and well and good and all, but who cares? What does this do to us? Well, what you want to do is you want to go back to those Lewis structures and assign polarity within the bonds. So you remember how to do that. You're going to need to look at your electronegativity chart. Get that in front of you, and what you're looking for is a difference less than or equal to 0.4. We're going to call non-polar. Greater than 0.4 to about 1.7-ish is going to be what we call polar. If it's polar, then you want to figure out the one that has the greater electronegativity and assign it partial negative, which means that that which it is attached to will be slightly deficient in electrons and be partially positive. Okay, so if we look at these structures up here, the nitrogen to oxygen bond is polar. So we would put partial negative, partial positive, partial negative, partial negative, because the oxygen has a higher value than the nitrogen and the difference is more than 0.4. Partial negative, partial positive, partial negative, and so forth. With the nitrogen hydrogen, that is also polar. Nitrogen now is partially negative, hydrogen is partially positive. Carbon-carbon, carbon-hydrogen, those are not polar. Those bonds are not polar, and therefore there's no polarity within the molecule. And then, of course, fluorine is the most electronegative element that there is. And our polarity would be distributed this way. So what you need to do is to go back to that handout, that lab handout. It's called VSEPR or molecular geometry or something like that. There should be about 6 pages of them if you're doing the one that I gave you. And go back and assign polarity into all of the bonds on all of those structures. And it will keep you busy for a while. Okay, so that then, having done that, did you do all your Lewis structures and your polar bonds on that sheet? And the answer to that should be yes. If it's not yes, then you need to pause this video and go back and do that. Okay, so moving forward, what we want to know is that there's a difference between a polar bond and a polar molecule. A polar bond means there's greater than 0.4 electronegativity difference between elements in the bond. Just the bond, okay? Polar molecule means there is a net dipole or a net separation of charge. And by charge, I mean polarity, because we're not talking about ionic bonds here. So the question then is, what is a net dipole? And in order to determine that, we need to learn about basic molecular shape. Okay, so basic molecular shape is given the term in its simplest application, VSEPR, valence shell electron pair repulsion. Okay, and what this has to do is with basic geometry or molecular geometry, which is why you see it under either VSEPR or geometry or molecular geometry. So in order to talk about this, we have to remember that in our normal XY plane, okay, we have 360 degrees in a circle. Okay, and so what this means is that the valence shell electrons want to be as far away from each other as geometrically possible. And remember, even though I have a flat piece of paper here, the reality of it is, for lack of better visual aid, is that life is not flat. Rather, it's 3 dimensions. Okay? So we're going to be looking at this in this plane, but also rotate it into this plane. So since I have a stamp on my apple, I'll rotate it. So this plane and that plane. See my little goofy guy there? Okay, so what you want to imagine here is we're going to start with having our Lewis structure, and we're going to have what we call areas of electron density. And the easiest thing to consider is having 2 areas. Okay, so you want to envision yourself, for example, Y, so Y is going to be you, and you want to envision holding your left hand and your right hand in a way such that the left hand is as far away from the right hand as possible. So for example, if you put your left hand in your right hand like this, you have 90 degrees difference versus 270. So that's not the best you can do. The best you can do is put your left hand here and your right hand here. Okay, so that the distance or the angle between your left and right hand is 180 degrees in this dimension and 180 degrees in this dimension or direction. Okay, now the other thing that you're going to want to do is take your hands, like I like to call these airplane arms. Airplane, just like an airplane when you were 3 years old or however old you were, right? So you've got you in the middle. You've got your left hand and your right hand, and then you want to turn this and pretend that you're on a ladder looking straight down at yourself. So here's you in the middle. If your left hand is here and your right hand is here, you still have 180 degrees in this dimension and 180 degrees in this dimension. In other words, it wouldn't make any sense for you to have your arms out like airplanes and then rotate them in some way as though you were standing on a ladder looking down at yourself and seeing that for some weird reason your left hand is here and your right hand is there. It just doesn't make any sense. And so my point is that your electrons, well, your left and your right hand are a model for what the electrons do. The electrons want to be at 180 degrees away in this dimension and what I'm going to call the hula hoop dimension. And that's what we call a linear geometry. 180 degrees will give us the shape of a line, or what we call linear electron geometry. Okay, linear is what you get when you have 180 degrees. Now what you want to envision is you standing in the middle, your left hand here, your right hand here. That's what the electrons are doing. But now it has to create an actual molecule. So you could imagine that your left hand now is grabbing something to bind onto. And then my right hand here is grabbing something else to bind to. And so you have to have a little bit of visualization on this, but you can envision you're grabbing onto something over here and grabbing onto something over here. And then that's the shape of the molecule. So there's no mystery here. We still have 180 degrees in all dimensions, and we end up with what we call a linear molecular geometry. Okay, so your job is to find all of the structures on your lab sheet that have two areas of electron density off that central atom and indicate that it has a linear electron geometry and a linear molecular geometry. So let me give you a quick example before we go on to the next segment. Carbon dioxide should have a Lewis structure like this. We look at the carbon in the middle. Here's one area of electron density. Here's another area of electron density. So our electron geometry is going to be linear. The molecular geometry is also going to be linear. If I take nitrogen gas, N2, choose one of these to look at. This is one area of electron density. This is another area of electron density. And therefore, linear electrons, linear molecular geometry. Go ahead and find those on your sheet. We'll also work through some of them in class, and then we'll pick up on the next segment with what happens when we have three areas.